Good morning, good afternoon, good evening from whichever part of the world you are. Today we have with us Dr. Professor Chrysothemis. She is currently an assistant professor at University of Leeds and a mining engineer with postgraduate studies in tunneling from National Technical University of Athens. In 2016, she has completed PhD in and in 2017, she was appointed as assistant professor at the University of Leeds to teach rock mechanics. And her research deals with geoengineering, innovative design, resilient and sustainable geostructures and infrastructure and their social impact. She has published more than 65 papers in international journals. And in September 22, Chrysothemis became the director of prestigious MSc Engineering Geology at University of Leeds, the first female academic. She is also active member of British and Greek Tunneling Society and was the general secretary. She in the past she has also held the position of vice chair at TAIym Group, and she is also a active member of ITACUS and ITS CET committee. And it is a pleasure to have you with us, Professor Chrysothemis. And people who are wondering what her name means, she has explained it quite in detail on her website. You can go through it. And over to you, Professor Chrysothemis.
Thank you so much, and thank you for your kind invitation to this lecture series. I'm going to share my screen now, and hopefully, it works.
I'll mute myself if there is some issues. I'll just let you know.
No problem. Thank you so much. So when I was invited, I was also kindly requested to talk about time-dependent behavior in tunneling, and I will take this opportunity and talk about not only time dependency, but time in general in underground engineering and how we design tunnels that they're going to last long, but also why. And this is another component of our field. So let's start. And I will be talking about time-dependent behavior of geomaterials in underground engineering. And geomaterial means, just to make sure that everyone is on the same page, any material formed by geological systems. It can be either considered soil or rock. And its origins is from Greece, and in Greek actually. It's called geoiliko, and actually means earth materials, so material coming from earth. And geomaterials are characterized by uncertainty, especially when we are dealing in underground engineering. I will come back to this chart figure that I like using when I explain uncertainty in geomaterials. And I have adopted someone else thought, Langford from 2013, about the different types of uncertainty. So there are levels. So we have the low, the medium, and high. So low is green. They're the things that we know that we know. Medium are the things that we know that we don't know, so we know their existence. And high level of uncertainty are there things we don't know that we don't know. So if we translate this in a tunneling scenario, the high level of uncertainty would be mainly geological anomalies and discrete hazards that we cannot predict and we don't know their existence. On the medium level, we have parameters that we can determine if we do more testing or if we do more investigation or GI campaigns, or for instance, stress regimes or time-dependent characteristics. And in the low level scenario, usually it's like when we go from point A to point B, this would be our alignment, the basic geological scenario, and if there is any past experience in an area or rock type. What we can do here is we cannot reduce the high level of uncertainty because we don't know its existence, but we can reduce the medium level of uncertainty, which is the yellow level here, and by doing more investigation and more tests. So I like using this term underground geotechnique because it can include all aspects of our field. It could be tunneling, rock mechanics, geotechnical engineering, and of course construction. And nowadays we are requested to do underground geotechnique and engineering, where we can focus or target societal sustainability. So what are the benefits if there is built-in sustainability or design and as-built, that I will be explaining in a few slides. And in order to do that, or by doing that, we also need to consider project success. So what does it really mean? How we design optimum and how we actually, at the end of the day, manage the risk. And this is a nice, I like this figure, AI or DALI, which is an AI engine, produced this for me when I asked like how we can envision underground world in an urban environment. And in many cases, in many urban environments and cities, this doesn't fall from what is happening in the real world. So it's a very complex world that we are dealing with. And why we go underground? Obviously, there are the obvious benefits. So, for instance, urban traffic, we can reduce that by going underground, or rural connectivity when we can connect, again, village A or rural city A to B. And for waste management, for water course, for parking, or other recreational activities that combine underground spaces or include underground spaces. And they're not so obvious for nuclear or hazardous waste. And these are a few examples around the world of such applications or their designs and concepts that they are actually into place at the moment. So we can design these structures that at the end of the day that we are designing them with the assumption that they will be last for 1 million years, not 100 years, not 150 years, but 1 million years, which actually we consider geological times. Or other not obvious, so how we can use the existing resources of underground space, such as constant temperature, for sustainable or greener solutions like geothermal energy. And this is what we are doing in Leeds, at the University of Leeds, actually. We had the visibility study of one of my MSc students a few years ago on how we can assess the geothermal potential even on a smaller footprint, such as a university campus. And right now, as we speak, there are boreholes drilled, and there is a pilot program where this idea can be implemented. And other not obvious applications like underground farming. Can imagine if you were in a remote area or an area where climate doesn't allow for such farming, but we can create microclimates underground where we can control more, and we can also produce such agricultural products. And this is important if you think of also other needs around the world. We keep saying that the climate is changing, and we need to do something, not only to stop that acceleration, but also to accommodate it. So, and by going underground, we talk about sustainability. Just going underground is a sustainable solution, some would thought. As we reduce the surface impact, we have lower carbon emissions, energy conservation with like constant temperature in underground environments, long-term resilience, waste management, research management, and the list can go on. And when we talk about societal sustainability, again, I will give the terminology. It's the ability of a community to develop processes and structures which not only meet the needs of its current members, but also support the ability of future generations, which comes to the time component, or includes a time component, the longevity, to maintain a healthy community. And most of us, or by now all of us, are familiar with these colorful boxes that United Nations, introduced back in 2015 to target these sustainable development goals, these 17 goals, in order to, let's say, contribute to this type of sustainability. And going back to our examples, let's see how we can target. For instance, from waste management, we can target SDG 3, good health and well-being. For water course, we can target clean water and sanitation. For geothermal energy, we can target affordable and clean energy. For rural connectivity, we can also target life on land by preserving the landscape, the environmental landscape. And another example that it's not only targets one SDG, but several, so zero hunger, sustainable cities and communities, responsible consumption and production, and of course, climate action. And as I said, we are going through an unfortunate period of like a lot of global warming increases. We hear a lot about extreme weather, of wildfires, hurricanes, floods around the world. And this is a trend and a graph that I keep using because you can see how things are increasing and become more and more frequent. And more increases means more CO2 emissions, and also temperature increases. And this 2% increase is actually the increase of the surface that is being monitored from the level of the temperature that was before the Industrial Revolution. So 150, 60 years now, even a little bit more. So that's the increase that we have monitored, and it's an alarming, or not alarming, like a strict alarming increase of things that will impact negatively our ecosystem. So, as I said, going underground means by itself being more sustainable solution against above ground solution or design, but is built in sustainability enough? It's just by going underground enough, or we need to reconsider and think through our design criteria, our design methodologies, etc. And what does success really mean? So let's see. It is being on time, being on budget, safely, and also sustainable. So trying to have longevity. And what are the main barriers and biggest enemies of going underground? And most of you know that by now. It's cost, which can come from cost because of the uncertainty at the beginning of the design, of the construction, or the disruption. And of course, the other main barrier is risk. So risk in design, in construction, and operation. And here I have put a table that I like using the presentations on cost overruns, where it shows that a lot of or many of the underground projects are over budget. And sometimes when things are wrong or can go wrong, can go really, really wrong, with the first example in the States where the budget cost 9 times more than the initial or the cost. And another slide that I like using from a project we did a few years back, it's how we can see that from this histogram, which depicts the number of incidents to the year, it shows that before and after the code of practice of the application that was back in 2006, the incidents have reduced. But you can go here in the pies and see here before the code was applied, and on the right after the code was applied. Don't know if you can see, but let me put my laser point. Yeah. So here is the after the code. You can see they're very similar. So, okay, the incidents have reduced, but the failure types that they reported before and after remain the same. And I'm going to go through the legend. So it's phase instability, overstressing of support, fire, crown failures, earthquake, or others. And the tunneling methods that were used, they're used before and are used now before the code, also remain the same when they reported the failure types. So we have TAIym, TBM, drill and blast, and cut and cover. So you can see very similar pies regardless of the application of the code. The number of incidents have reduced, but the reasons remain the same. So that should put us into perspective. During construction operations, some other data. So you can see the tunnel types. We have road, metro, rail, and hydro. We have road and metro, the ones that they serve or govern the failure types, and the excavation method, as we saw before, it's TAIym and TBM methods were reported during construction incidents are. And during operation, let's go here, fire, earthquake, overstressing of support, crown, feed works, and others. During operation, there are failure types, and we have fatal incidents when fire takes place. This is the biggest enemy. So coming back to uncertainty, uncertainty doesn't come without a cost. So remember that, what I'm going to say just now, that in a conventional or an TAIym, let's say, the tunnel, the excavation cost usually remains stable. So regardless of the or unaffected of the, let's say, quality of the ground that we are dealing with. And here is the cost. So the support cost is the one that governs the construction cost. And if we consider that the construction cost, which involves excavation and temporary support, governs that cost, covering 60 to 70% of the total cost, then we can see how designing a good support system can be very beneficial in our cost, on staying cost low on budget. So let's see now this graph that shows how we can be more sustainable during the different stages of a project. So planning stage, design stage, construction stage, and operation stage. And as you can see here that the opportunity to adopt sustainable solutions reduces as we move forward to the project. And there is a cost, right? How more sustainable can we be? And as we, again, move through the different types, stages of the project, the cost can increase. So the idea is to try to find the optimum point where these two can meet, and with no further cost, we can be the most influential, let's say, influentially sustainable we can be to a project. And I will be closing this sort of introduction on why we care very soon. But let's talk about something that actually I was told when I was a university student, and a professor told us that no two rocks are the same and not all the ground behaves the same. You can take a similar limestone from one area to a close by area and the mechanical behavior can be different, or the same limestone, let's say geological, or the same lithology, and you can test it under different conditions, let's say stress conditions, and you can see that it would behave differently. So we need to be very careful when we are dealing with different behaviors, because they require different strategies and also different design methodologies. And in underground environments, we are dealing with complex and demanding boundaries and scales. And these are all examples from rural applications or projects from that I have visited or worked around the world. And you can see mines, you can see underground caverns, you can see old railway tunnels, experimental tunnels, road tunnels, etc. And other urban areas where, the design methodology needs to be very carefully considered, because you need the minimal disruption, both in traffic, but also in movements and vibrations. So the main challenge is that tunneling is a dynamic engineering multi-phase problem, which is usually project dependent. Why? Let's see why, and then let's explore the different phases of tunneling. So design optimization and risk management. What does it mean? It means first, understand the behavior and performance of our system, predict failure, and then avoid failure, but ideally not over design. And almost everything starts from a crack, is what I usually say also to my students. And failure usually occurs when stresses are higher than the strength of the material. But sometimes failure can take time, okay? Which brings us to today's theme and topic, dealing with the fourth dimension, time. So let's see a few real-life examples of delayed failure. Delayed failure can be seen anywhere. We looked at from rock slides to hour-shaped pillars in mines, to sinkholes, to other instabilities in foundations, to landslides, to rock falls, to big mudslides, or underground environments like spalling here, dog ear, etc. And the materials can be different. Or here, you can see under construction tunnels where they have shown delayed failure in swelling, squeezing, time-dependent squeezing, or big convergence that they have occurred over time. And different behaviors require, again, different strategies and different methodologies. So let's define time-dependent phenomenon. What do we mean? So there can be different phenomena that they can occur over time. So creep, which is the time-dependent deformation of rocks and rock masses subjected to constant stress, less than the short-term strength. Consolidation dilation, which is the time-dependent volume change of shrinkage or creation of pores. Swelling, which is again the time-dependent volume increase caused by absorption of water in the zone close to excavation, and usually it appears as a heave in tunnels. Stress relaxation, which is the time-dependent stress decrease while at least one principal strain is confined and remains constant. You can see the R-shaped pillar relaxing, or strength degradation, which is the time-dependent strength loss, chemically assisted and driven by stress corrosion. I'll be focusing in this presentation on grip, on strength degradation, and stress relaxation. So what does it mean? So this can be what we can see from an extensometer in a tunneling environment. This is the displacement over time, or the convergence over time, and this is the time. So it's a function of time, let's say. What we see there can be a cumulative result. It can be either because time-dependent phenomenon can act either individually or in some cases simultaneously, or one after the other, especially when we're dealing with soil or soft rocks, where consolidation can kick in, and then we can also observe creep behavior. So where one stops and the other starts, that's a big question, and we can actually see that in the lab by doing different types of tests that unfortunately take a lot of cost and a lot of time, but it's worth doing. So let's back up a bit, and I'm going through this this graph that I will be explaining again the phenomenon. A phenomenon, a time-dependent phenomenon, can be either due to a change in the state, or a change in a property, and according to its reversibility, can either be considered elastic, inelastic, or irreversible. And the physical response can be considered, as we saw before, creep, contraction, dilation, relaxation, degradation. The physical mechanisms, what is happening in the microstructure, can be either due to solid rheology, the damage, the discontinuum elements, or any physical chemical changes as it is happening in swelling. And the rate can be controlled either by chemistry, fluid mobility, stress deviator, stress conditions, temperature, pressure, humidity, or confinement. So looking at this and putting this into different combinations, we can end up having creep, stress relaxation, or strength degradation. This is what I will be talking a little bit more today. So it is very important to understand that geology matters, and it matters because it is very important to understand how the different geomaterials that we're dealing with were formed and under which conditions they were formed and created. Because a ductile potasse, as you can see here, it can have a different behavior over time, which is going to barrel at the end and show a plastic formation, than a brittle limestone that it will accumulate damage in its microstructure, and at the end of the day, it's going to fail in a sudden manner. And how we can see that different behaviors in the lab scale, where we can actually test this type of mechanisms, is by changing our testing boundary conditions. So let me take you a step back. So this is, as you can see, an axial stress strain complete stress strain curve from UCS test in a brittle material, let's say this limestone. So at the beginning, as we test our sample in uniaxial conditions and we increase the axial load, we have the crack closure until we load the sample a little bit more, and we have the first crack growing due to our load application. And as we move a little bit higher with the load, we can create more damage, more cracks that they will interact with one another, up to a point where we have the crack damage threshold, after which we ultimately are going to lead the sample into failure. This is going to be the strength of the material, the UCS as we know. So how do we change these boundary conditions? By either holding the stress or the strain constant at the load level, which is below the UCS, the strength of the material. If we don't hold it before, we're going to fail it instantly. Okay, so by either holding the stress constant, we can observe creep behavior, or by either holding the stress constant, we can see the stress relaxation behavior. Here is another figure what these two tests mean. So holding the or loading the sample up to a point below the UCS and holding the strain constant, as you can see here, and we can see how the stress relax over time. And here the creep or static load test, loading the sample up to a point below the UCS, where we hold the stress constant. The stress remains constant over time, and we can see how strain behave over time up to failure. Again, to remind you, everything starts from a crack in most of my world, or the things that I'm doing, almost everything. Okay, I mean failure or damage. And here is another representation of the different type or stages of both creep and relaxation. Both of them can be characterized by three distinct stages. They have like some kind of opposite behaviors. So the first stage, we have increasing deformation, axial deformation, let's say, with a decreasing rate. Then we have a increasing rate with a more steady rate up to failure, which is the third stage. Where relaxation, we have relaxing of the stress with a decreasing rate, and we have a more steady rate of the stress relaxation up to the point where we find an asymptote where no more stress relaxation takes place. So here are a few examples of limestone. We need to understand first how the material behaves in static conditions, so instantly. That's why we do UCS testing and triaxial testing. And then we can move on to, so we know our thresholds, to relaxation testing. And this is examples that you can find on the papers published on relaxation testing, where you can see these three stages, how the stress drops at the beginning of the first stage, and then it has a more consistent rate where it finds an asymptote. And you can see also the radial strain changing over this phenomenon. Or static load testing, where here, this is where we start holding the stress constant, and we see how the strain changes over time. From this type of test, the other thing that we can get is also the strength degrade, how the strength will degrade, how it will decrease over the time, where we can get the long-term strength. So as you can see in this stress strain graph, you can see the UCS here, and you can see the ultimate point of the long-term strength, which is can never go zero, because there will be no strength to the materials, and there is not going to be any ground in our feet if that was happening below our feet. So CI, the crack initiation, would be our main or ultimate long-term strength. So you can see here by holding the stress constant when it fails over time, and this is how the UCS, the strength of the material, the short-term strength can decrease. Let's see now why it is important in tunneling and go a little bit deeper to the topics, today's topic. These are unfortunate situations that were recorded many years back, a few decades ago, in Yakambu Tunnel, that you can see the remaining parts of a TBM here, where the engineers, designers, practitioners there had to excavate this part of the tunnel. You can see here like more than 1 meter convergence. And this convergence took time to happen. So the tunnel was moving forward, and at the back of the tunnel, this was happening. So convergence, this inward movement as we excavate, can take place because of the tunnel advancement. Okay, as we move forward, we disturb the stress conditions, we disturb that in situ environment, so we end up having some movement. But also it can be due to the time-dependent behavior and potential of the geomaterials around. And a way of trying to capture this phenomenon, and not just in rock mechanics or geotechnical engineering, but any phenomenon that can change over time, is by using one of the ways rheological models that consist of mechanical analogs. Mechanical analogs are springs, dashpot, sliders. If we put them in order or in parallel or in different combinations, we can have different mechanical behaviors, and we can represent different mechanical behaviors. Other ways is to build very sophisticated constitutive models and laws. Or power laws. So this is one that is used in codified also softwares easily, and you can modify or you can play around and make your own models that can represent better what you see in situ testing or in lab testing, because they need parameters. So if we put an elastic spring and a plastic slider, dashpot, and a viscous dashpot in parallel or in series, as you can see here, we can have a viscoelastic, this time-dependent component added to our system. And by playing around, we can end up having the different stages of creep represented or simulated, or this can be used for swelling behavior or any type of behavior that changes over time. Okay, it's not just for creep, it's for anything. It only needs to have the right parameters. Okay, let's see now this convergence, how it's being changed, or how it changes as we advance the tunnel, and then if we have a time-dependent component. Here, as you may all, or most of you are familiar, when we are in front of the face, we tunnel in this way. This is a cross-section of the tunnel. Our in situ stress are equal to this internal pressure because we haven't affected the system, okay? And close to the face, this internal pressure, that is a pseudo pressure that we have invented in order to understand the support pressure that we need to add back to the system to avoid failure, starts to be lower than the in situ stress conditions. So we have an unbalanced situation here. And when we move away from the face in the excavated tunnel now, this internal pressure is 0, okay? So the question is, when do we add our support and how much load this support should take over in order to optimize the design and obviously avoid any overstressing of support. As we saw, it's a very main type of failure in our construction incidents when I show you at the beginning. And this is obviously a problem that is always that always refers to where our tunnel face is. So we use this convergent confinement method many times because it gives us an idea of this reduction of the internal pressure in regards here to the in situ conditions. And if our material was behaving elastically, then we would have a linear ground reaction curve. This is how we call this, okay, to show the decrease of internal pressure. If our material behaves elastoplastically, which is usually what we assume of, then it will deviate at some point from the linearity or this, how this decrease of the internal pressure would look like. So and this can be when we don't consider time or our material is not time-dependent behavior. When we do consider time dependency, we can have either viscoelastic behavior if our material is behaving viscoelastically or viscoplastically, similar idea. But the thing is that now our U, which is the displacement, is a function of time, okay? It's not just a function only of the tunnel phase, it's also a function of time, as you can see here. And the other thing that we use as a tool when we want to represent this 3D tunnel problem into 2D conditions is the longitudinal displacement profiles, or we call them LDPs. So in this LDP here, which you can see, again, in reference of the face, how much displacement has occurred in front of the face because we have already disrupt and disturbed our material close to the face, and how much would be our maximum displacement on convergence away from the face, the excavated tunnel. If we know this LDP in regards to where our tunnel face is every time, it is a very good tool to estimate our displacement and then design our support system. So let's talk about now delayed deformation. We are looking again at the tunnel where we advance this way. This is a cross section again. And let's consider, I'm just going to go a little bit back here, make it more simple so everybody can follow. That if for a material was behaving elastically, not even elastoplastic, like the simplest condition, isotropic, then we can see that what we usually say is after 2 or 3 diameters away from the face, as you can see here, we'll start having the convergence being steady, so we'll have reached our maximum displacement. In cases where we haven't reached our let's say maximum displacements where because of time our material behaves time dependently, we will have underestimate our maximum displacements because we will keep having movement, as you can see here, show up with primary, secondary, let's say, stages of grip up to optimal, this critical time where we can end up having a failure or permanent failure. And you can read more about this idea in our paper showing in the screen about that. And again, by using these mechanical analogs or rheological models, we need to make sure we are using the right parameters. So this is why it is important to do such tests that take cost and time in the labs to get actual parameters, because we can backfit these curves, these lab curves, and get the parameters we need for these viscoelastic models, that at the end of the day, we can use them to codify solutions like fine elements. Some of them have that, like Fluxys, or FLAC 2D, FLAC 3D solutions, and Itasca software, where you can incorporate these dynamic solutions in there, or time-dependent models. And this is an example of it, again, from the same paper. It shows a 2D tunnel, like an axisymmetric tunnel, where we had two cases. It was a parametric analysis based on time-dependent behavior of a drill and blast and a TBM excavation, depending on how long the excavation cycle was, if it was 1 meter or 3 meters per excavation cycle. But also what we modified in this model was also the duration of its cycle. So not only will we have the time-dependent component, as you can see in these LDP curves, okay? This is if we had the elastic behavior only, and this is the ultimate viscoelastic behavior. But what was important to see is like how we can get there depending on our duration of each cycle. If it was obviously 2 hours, which is very short and unrealistic, to 8 hours shift. Okay, so we played around with this model, and we did our tweaks and modified it in order to capture what is happening mainly in real cases. So this was the case for drill and blast, and similar to TBM, you can see that it can take longer time to get to the maximum displacement, but in less deformation, because we have a very short excavation cycle. So we don't, with 1 meter instead of 3 meters, so we don't disrupt too much the behavior. So, you know, there are also things to consider when we design or we choose our tunneling method. Okay, so another aspect of time dependency and how we're going to deal with it, especially when we're dealing with nuclear waste repositories, is that they have a design lifetime on 1 million years, which is geological scales. Let's see how we can deal with it. And just to remind you, that's another aspect and impact of our underground engineering. And many places around the world are either constructing, either operating, or either designing this type of facilities. And it's very, very important to understand this long-term behavior. And here I'll be talking more about strength degradation. And you can see here, this is a graph again that shows over time on the Y and on the x-axis how the strength as a ratio of our stress divided by the UCS is decreasing or degrades. So you can see these are different thresholds related to the crack damage, which is usually 65 to 85% of the UCS, or CI, which is 30 to 40 or 30 to 50% of the UCS. That above the CD, we have inevitable failure that's going to happen really, really short. These are examples from static load testing in the lab. Between these two thresholds, things will fail, but will take longer time. And below CI, things shouldn't fail because these will be tested in a lower stress regime than the long-term strength, as we saw before. And another way of looking at that, different types of results. You can read again more about in the following publications on how we actually can utilize not only our data that we would do in the lab. Many other scholars have published such results, and we have managed to combine them together and give some conclusions about different types of rocks, like if it is sedimentary, metamorphic, or igneous, and how they would behave over time. So one of the works that we did a few years ago was introducing the long-term strength model. So using one of these rheological models that they can be found in codified software here in Tasca, and how we can tweak it not only to resemble creep behavior, and at least from the first two stages of secondary and primary, not tertiary, but also how we can combine the long-term strength, how the strength can degrade over time. So, and it shows here, for instance, some cases from when we have an instantaneous response to after 7 hours when failure can happen, and what this means. Oops. So another project that I'm currently working in the UK is trying to understand the materials behavior that they're considered to be host rocks for the GDF, Geological Displacement Facility in the UK. And because of the geological, let's say, restrictions we have in the UK, we don't have plenty of geological or lithologies. We are considering to host this in the lower strength sedimentary rocks. So there are a wealth of them around the UK. So we are testing them in our lab in Leeds with one of my PhD students, Thomas Berry, which we're actually looking at self-sealing over time, because these lower sedimentary rocks are characterized by either discontinuities or joints or other types of discontinuities, obviously bedding, etc., that can that eventually over time they will seal. So as this material can have different mineralogies, we're looking how also minerals can impact this type of behavior. So this is currently under investigation. And the last bit of my presentation, and hopefully I will be over in a few minutes, is the other component of time. What do we do when we are exceeding or close to exceeding the lifetime of an existing project? Are we prolonging it? How we're going to maintain it, etc. And this is a big issue in the UK as well, and around the world, because as you can see here, this is I put together this graph to show design lifetimes of different infrastructure, and you can see underground mines or tunnels are designed for 50, 100 years, and a lot of them have exceeded, or if this was the lifetime of an asset or an infrastructure, you can see here how the risk of failure degrades over time, and then in the wear out period, we have an increasing risk of failure. So early life, decreasing risk of failure. Useful life, we have a constant failure rate, and then how things are going up. And a lot of our infrastructure, old infrastructure are approaching or are in this period. So they will need inspection and maintenance. And this brings me to this last example about the Victorian tunnels, that this lady here, Queen Victoria, had a vision in expanding the railway network in her times from 100 miles to 6,500 miles, and this yielded the construction of 215 railway tunnels, where this guy here, you might have heard of him, Mark Brunel, was the pioneer of seal tunneling, was the engineer in a few of them. So let's see this tunnel, which name is White Ball, and was designed by Brunel. It's in Somerset. As you can see, its lifetime is it's 180 years now. And what we are requested to do is how we're going to enlarge it, because right now the National Railway is trying to electrify the network. So the current designs or tunnel design dimensions are not let's say suitable for these requirements. This tunnel is built on, again, sedimentary rocks, soft rocks that can be problematic in terms of support. So how do we design the tunnels? And here was a study we did a few years back with different enlargement percentage. So trying to enlarge the tunnel from 20% to 10% in terms of diameter, but also the excavation cycle. So how fast we go, or how conservative we go, and also the different types of lining in order to minimize the movement that we would end up creating. And there, I didn't mention that, sorry, but this type of machineries that this was built on our numerical model, where we actually we use these as TBMs. Here, this is one of the methods where you can put that, and below and above you can actually do the enlargement, and you can have even traffic going below your panel, and it progresses as a TBM, advances as a TBM. And a final study we're working on, this is two final tunnels, sorry. This is Upperton Tunnel, again designed by Brunel, and we were looking to see in order to understand the movement that it was occurring during these almost 175 years now, how it has been created. So the time-dependent component of it, by doing back analysis numerically, looking at the initial designs, the actual scans that show the convergence, and how we can back analyze this type of behavior. This paper is under review, and this is the final study we're using. Is like, how do we use these modern technological advancements, obviously the AI, in order to avoid manual defecting or manual refurbishment, in order to assess the severity of different areas in this type of tunnels. They are brick wall tunnels or stone wall tunnels, by using LiDAR or scans and cloud points in order to assess, again, the areas of severity. And this is a nice video that explains that, and you can find all that the Smith et al. Publication. There you can see the video. Okay, so first we have the input of the point cloud from the LiDAR data. We unroll and rasterize the tunnel. Then we determine the dimensionary block joint locations and where the damage location are. Then we have the We try to fit an undamaged surface and calculate the different offsets, the convergence, let's say, and then determine the defect severity. So that's the process of how we are analyzing this, so we can minimize the exposure also of the personnel to do that, to assess this type of situations and conditions. These levels of severity is the movement, so 20 millimeters or 50 millimeters, and these are from National Railway guidelines. So some take-home messages. So sustainability is built in, but it can also be obtained. No two rocks ground behave the same. Different behaviors require different strategies and design methodologies. Everything starts from a crack, or almost everything. Time effects can lead to delayed failures. Strength and material properties can degrade over time, and we need to consider that in our design. For existing underground infrastructure, how we can prolong their lifespan, reuse them. For new underground infrastructure, is it time to actually reconsider new design guidelines? And at the end, project success requires a sound risk assessment plan, and a risk management requires design optimization. And these are my references, but most importantly, these people and group of students have been, I would like to acknowledge for their contributions, and also some of other collaborators and colleagues around the world. So thank you. And I should say thank you for your attention. And I'm not sure if I pronounce it correctly, but I will try to say it. Danyavad. Thank you.
Thank you very much. And we will move ahead with the question and answer session now. If anyone from the audience have any questions, please put them in the chat box and we will take it. If it's fine with you. I believe today's webinar was so good that I don't see any questions. I will just wait for another 1 minute or so.
That's okay. I hope you enjoyed it.
Mr. Abhinav, I will request you to put it in a chat box. That will be better for us and every one of us. We'll just wait for a 1 minute or so. If someone is willing to put out their questions in the chat box, we'll go ahead with it. And I would like to congratulate you for the wonderful webinar that you have conducted.
Thank you, and thank you for the invitation. And I think I put my contact information at the beginning of the slide. So if you have anything, you feel free to contact me directly.
Sure. Again, we will reshare it with all the members. So if anyone has any request or any kind of questions or queries regarding your webinar, they will definitely try to contact you. Once again, perfect. Thank you, Dr. Chrysothemis, for a wonderful webinar on time-dependent deformation in tunnels. I'm sure that your experience will be very useful for everyone, and I hope our student members have got a clear idea about today's topic. Even though the Diwali festivals are underway in India, we had our largest turnout of the attendees today. That's because of your wonderful presence in the tunneling industry and the very excellent topic. I would like to inform you all that our past webinars are available on the YouTube channel, and this webinar will be uploaded shortly. If you're not a member and want to become one, please kindly contact us for the details. Before signing off, I would like to request all the members to renew their membership for the 2024 to ensure the timely benefits. I would also like to invite new members to be part of the TAIym, which is solely focused on bridging the experience of the professional working on different projects and also act as a platform to share the technical expertise in the field of underground construction. And there is all these many additional benefits of being a member. So grab a chance to be one today. Once again, thank you, Dr. Chrysothemis, for sharing your experience, and thank you all for joining. Have a great rest of the week. Stay happy, happy tunneling, and happy Diwali, all of you.
Thank you.
Dhanyavad.
Bye.